test. Consider our respiratory disturbance index example again. A reasonable strategy would be to reject the null hypothesis of our sample mean respiratory disturbance index was larger than some constant. Let's label that constant C. C will take into account the variability of X bar. Typically, C is chosen so that the probability of a type 1 error rate, this probability we label alpha, is a low number. 5% has emerged as sort of a benchmark in hypothesis testing. So to repeat, alpha is the type 1 error rate, which in other words is the probability of rejecting the null hypothesis when in fact the null hypothesis is correct. A bad thing. We don't want to make these kinds of mistakes. But as in our court of law example, we don't want to set this rate too low because then we would never reject the null hypothesis. Let's see if we can choose this constant C so that the probability that we reject is simply tolerably low, say 5%. The standard error of the mean is 10, the assumed standard deviation of the population, and here we haven't drawn a distinction as to whether we've estimated or this is just a number that I've given you, divided by square root 100 as the square root of the sample size. That works out to be 1. Here I just created the setting so it conveniently worked out to be 1. Under the null hypothesis, where under H naught mu is equal to 30, the distribution of the sample mean, x bar, is normal with a mean of 30 and a variance of 1, which we just calculated as the standard error, the square of the standard error of the mean in the line above. So we want to choose the constant C so that the probability that x bar is larger than C under the null hypothesis is 5%. So remember, the 95th percentile of the standard normal distribution is 1.645 standard deviations from the mean. So if we set the constant as 1.645 standard deviations from the mean under the null hypothesis, we will have achieved a cut point so that the probability that a randomly drawn mean from this population is larger than this is 5%. So in this case, it's 30, the hypothesized mean under the null hypothesis, plus 1, the standard error of the mean, times 1.645, the number of standard deviations from the mean that we're considering, which in this case works out to be 31.645. So, just to reiterate, the probability that a normal 30 with a mean of 30 and a variance of 1 is larger than this constant is 5%. So the rule, reject the null hypothesis when you receive an average larger than 31.645 has the property that we will reject 5% of the time when the null hypothesis is true. Again, 5% of the time in the instances where the sample size is exactly 100 and the standard deviation of the population is exactly 10. In the previous slide, we reverted the calculation of the rejection region, C, back to the original units of the data. However, I hope you got the gist from the problem that basically whenever you were testing greater than, if the sample mean is more than 1.645 standard errors from the mean, from the hypothesized mean, you would reject. And there was nothing particular about 30 and the standard error of the mean of 1. So instead of calculating this constant back on the units of the original data, we tend to convert our sample mean into however many standard errors from the hypothesized mean it is. So take this specific example. If our observed sample mean was 32, our hypothesized mean is 30, and our standard error is 10 divided by square root 100, where in a real problem, the 10 would be estimated from the data, so it would be the sample standard deviation. This works out to be 2. This is greater than 1.645. The chance of this occurring is less than 5%. So we're going to reject the null hypothesis. I should reiterate, the chance of this occurring under the null hypothesis is less than 5%. So we're going to reject the null hypothesis in favor of the alternative hypothesis. So I've just simply written out this rule again here on the final line. We're going to reject whenever x bar minus the hypothesized mean divided by the standard error of the mean is greater than the appropriate upper quantile that leaves alpha percent in the upper tail.